So today I'll be going over the HDF5 tutorials repo, and within that, some of the notebooks going over cloud stuff. So if you're not familiar because you weren't here last week, the HDF5 tutorials repo is a new project we're setting up designed to guide someone who might not be familiar with HDF5 or even, how to write a C++ program and bring them up to speed where they'll know what resources to use and what options they have when trying to work with HDF5. So to get started, I'll pull up the repo. At first I had these notebooks already set up, but since I'm using a new computer now, you'll get to see me do it from the start. Right. And so the way this is designed to be used is in a GitHub code space, which I'll set up now. Here under code spaces. Anyone can create a new one, so this can be used without having to download or install anything on your own local machine. This will take about 15, 20 seconds to set up, and you'll see on the left over here all of the files, including the Jupyter notebooks that we'll be going through today. Let's see, while that loads, the first one we'll be going through is going to cover HSDS, the highly scalable data service. HSDS is a web service that implements a REST API for working with HDF5 files in the cloud. And HSDS isn't tied to any particular backend storage. It can be S3, it can be local file system, it can be min.io. You've got a lot of different options with it. This diagram shows its architecture. Client requests are satisfied by one or more service nodes, which then on the back end satisfy the requests through data nodes, which talk directly to the object store that's being used by the particular setup. In this case, the setup will use the local file system as the backend storage just to demonstrate how HSDS works and how you can communicate with it through Python. So let's see, first, I believe running this cell will prompt me to set up the environment for the notebook. We'll choose to do Python, the HDF5 tutorial environment. And this will take a moment to connect to the kernel. So what's going on here is we're setting up the endpoint to connect to a server from, in this case, the local host, as well as configuring an expected username and password to access the files we'll create. We've told HSDS to use as its root directory this HSDS data folder, which is where we'll find later on all of the domains we create within HSDS. Here we're going to configure HSDS using hsconfigure, which is part of the HS tools, a set of command line tools included with h5pyd. h5pyd is a Python module we'll be using to actually communicate with the server HSDS. h5pyd, from the name, you might figure that it's very similar to h5py, which it is. It's essentially h5py's interface, but under the hood, all of the operations are implemented as requests to an HSDS server. All right, our server is configured. Let's see that it's running correctly with the command line hsinfo. Yep. Server state is ready on our endpoint with the username and password we configured, version 084, and also our h5pyd version 0810. So now our server is running. We can check and use the command line tools from h5pyd to actually create a home directory and then a home user directory where we can store our domains we're going to create. Now, instead of using the command line tools, we can actually, like we would during, actual use of h5py, do it through a Python program. We'll import h5pyd the module and now create, just like h5py's interface, create a file in write mode, create a data set, and write some data to it. Finally, close the file. And because we configured HSDS to use our local file system on the back end, well, this is a point which might be a little confusing because This says that it's not a file in the local file system, but a domain in the HSDS service, which is true because we could have configured HSDS to, work with S3 or MinIO or whichever backend. In our particular case, it is, since our file system is the storage backend, there is actually a file on this file system corresponding to it, but it's not where you'd expect under this home VS Code foo path. See, that path doesn't exist because it's stored under the root directory we gave to HSDS earlier. Here we make a request to HSDS to that domain, and we see, this domain does exist, has a root group with this ID. We can see the owner of the domain, when it was created, and some information about it, the available compressors. But if we want to find it on our local file system, we'll have to look under that root directory we created earlier, the home HSDS data. If we look under here, we'll see, right here, home VS Code, HSDS data, the root directory, HSDS test, and then the two folders we created earlier, home and VS Code, and finally the domain we created, foo.h5. There are a few more very useful command line tools with h5pyd. There's hsls to list out all of the objects within a domain. So within the domain foo.h5, we have our data set named dset with dimensions 4. And to get statistics about a domain, we can use hsstat. Again, we see the user that owns it, its group ID within HSDS, and some information about its size, allocated bytes, and so on. And here's where the power of h5pyd and HSDS really shines, is that h5pyd, if you import it as h5py, then you can, with pretty much zero modifications to your program, have this Python program that was previously using h5py to operate on a local file that's now using h5pyd to talk to HSDS and work with HDF5 files on the cloud. And so this program is going to generate some random data according to the Ornstein-Uhlenbeck process and eventually write that to a file. So we import h5pyd as h5py, and all of the same interface is going to work the exact same way, h5py.file to open a file, create dataset, write to the attribute, and write to the dataset itself with these values we generated. You can see that it ran all right with these parameters, 100 paths, 1,000 steps, and some parameters for the random generation. And now we'll use hsls again on this new data set we created. We see all these attributes attached to it in that program. And if we want to visualize the data we just generated, we can do that using matplotlib, exactly the same as we could if we had done all of this with h5py on our local machine. Here's a nice graph showing that random data. But if you're not starting off using HSDS, you might have an HDF5 file on your machine that you want to put in the cloud. You can do that with hsload to take this local file, OU process, and turn it into an HSDS domain with the same name under those folders we created earlier. Now use hsstat, see that it is uploaded to the server correctly. Interesting. I'm not sure why it reports the size as 0. HSLS show attributes. Yeah, we can see that the domain on the server still has the same attributes and the same values. This might be an issue with hsstat. I'll have to investigate that. Oh. And we can do the same process in reverse and bring a domain on HSDS to our local file system as a regular HDF5 file using hsgit. And this h5diff command tool checks to see if these two files are the same after having been sent to the server and brought back, and it outputs nothing, meaning they are the same. So nothing was messed up or corrupted in the process. And that is HSDS. This notebook should serve to bring someone who, has no idea what that is, show them what it is, how to use it, and how it can benefit them. And this next notebook, number 6, shows off another way to interact with HSDS, which is the RESTful. Well, let me start this first cell now because this one takes a few minutes to clone the HDF5 library. Right. The RESTful is a vol connector for the library. The virtual object layer, or vol, is a layer in the HDF5 library which allows the implementation of all the API operations to be changed, but keeps the interface the same, similar to how H5PyD, keeps H5Py's interface, but speaks to HSDS instead of the local file system. The RESTful is a very similar thing, but for the HDF5 library itself instead of H5Py. So this first cell is going to install HDF5. The reason we're cloning HDF5 again here, rather than using the pre-installed version, is that the vol layer was only implemented in 1.12. So the RESTful needs a newer version of the library. So this is going to clone HDF5, build it, then clone the RESTful and build the RESTful.
So I have a question. Why is that instance running the old version of the library? Is that what you're saying?
Right. The Jupyter notebooks by default run an old version of the library.
But why? They don't have to.
I'm guessing that the HDF5 default version comes from a package manager. I couldn't tell you. I'm not sure though.
All right. Okay. All right. Thanks.
And so once that finishes running, we'll have the full connector and a version of the library that can run it. And with that, we can take a regular C++ program, change a few lines, and then we'll be using it to work with files on the cloud. So those few changes that we do need to make are to initialize the RESTful connector, terminate it at the end of the file, both of which are just one-line changes. And then when we open the file, we'll need to use, there's some output from the cell above. When we open our file, we'll need to change the file access property list to tell it which vol connector to use, in this case, the RESTful. So H5 REST init is going to initialize the RESTful. This H5P set FAPL RESTful is going to modify the file access property list and tell it that when we use this, we'll want to open and operate on this file through the vol connector. Then at the end of the program, we need to terminate the RESTful with H5 REST term. And that's it. You can have some giant program, and these 3 little changes are all you'll need to do to change it to work with HSDS. Looks like the installation is done. So I should be able to run this to write the program to a file, build it, and run it. You can see that it ran okay. So now this C++ program, using the library's regular interface, should have created a data set on HSDS. You can see it's all there, same attributes and values as usual. And one feature which has a unique implementation in the RESTful is multi-read and multi-write. This is a new API interface from 1.14, which allows users to specify multiple data sets with their own selections, their own memory types, their own selections on each data set, to read from. And the advantage of this is that depending on which vol or VFD is implementing these read and write operations, when being given multiple data sets at once, it has the chance to optimize those operations. In the case of the REST vol, because all of these reads and writes are being implemented as requests to the external HSDS server, being given multiple requests at once allows it to asynchronously send out multiple requests to avoid having to, send out one request, wait for it to come back, process the response, and then send out the next one. And just by using this read and write multi-interface, you can get faster times by a factor of up to about 2 times with, say, 6, 7 data sets. So this program right here is demonstrating the read and write multi API. You can see that write multi takes in a parameter saying how many data sets to read from, and then arrays containing the data set IDs, type IDs, selections, and so on. The same information you would normally give to a read or write command, but now in an array form to specify multiple targets. So we'll compile and run that and see that hopefully it succeeds. All right, and then HSOS to see that this domain now contains 2 data sets that we successfully read and wrote to. And then the last cloud notebook I'll be going over today is S3 and the cloud. So this notebook, unlike the last 2, does not focus on using HSDS, but just on using S3 buckets directly with the ROS3 VFD. ROS3 VFD stands for the read-only S3 virtual file driver. The virtual file driver is, you can think of it as being very similar to the vol layer in that it provides a way for library operations to keep their interface the same while changing how they work under the hood. In this case, the ROS3 VFD is going to route read operations to read directly from an S3 bucket. And this can be very convenient for you if you have, say, a regular HDF5 file that's already in an S3 bucket, and you just want to read from it without having to go install anything external. Because the ROS3 VFD already comes with the library itself. All you need to do is enable it at build time, which in CMake can be done with this HDF5 enable ROS3 VFD option. And this is going to take a couple minutes to clone HDF5 again. So we'll move ahead for now. So we can check to see that this S3 bucket contains the same file we've been working with before, with all this information about a superblock, the groups it contains, an attribute. Let's see, is it done installing? Yes. All right. So now we'll have a program this is a C program. It's going to use the ROS3 VFD to read from that file. And similar to when using the REST vol, the only change you need to make to use the ROS3 VFD is to modify a file access property list and provide it with a couple of options. In this case, those options are parameters for S3, telling it which region to read from, and the URI of the file to access. Because this file is publicly available, we don't need to provide any authorizations, so no secret ID or secret key in this case. But if you have a secure file you want to read from, that's also possible. We'll use H5P set FAPL ROS3 to configure this file access property list to tell it to read from S3. And then the rest of the operations, opening the file, opening a data set, and reading from it, all use the normal library interface. So we'll run this to create the file. Then build it and run the program to read some values. And so now we've got a third way to read from HDF5 files on the cloud. Like the name says, this one is read-only. So if you want to write files directly on the cloud, you'll need to use HSDS or a different solution. But for this, it works quite well. But the ROS3 VFD is not just usable through a C program. If you want to use it through Python, you can also do that. This is another situation where you will need to enable it at build time for H5Py. So we'll clone H5Py and build it against our HDF5 library. The way you actually enable ROS3 with H5Py is to build H5Py against an instance of the HDF5 library that has ROS3 enabled. So we'll build this against the HDF5 we set up at start of this notebook, which has ROS3 enabled. And once this is done, we'll have an H5Py module that can use ROS3. So here, H5Py, we provide those same arguments to the library, to ROS3, telling it where to find the S3 file, in this case, US East 2. We still don't need to authenticate. And to tell H5Py that we're using ROS3, all we need to do is to provide this driver argument, as in virtual file driver, and tell it that we're using ROS3. Then we can directly open it like normal, H5Py file, open the data set, and read some values. And once that runs, we see that, scroll too far. We see that the values we read are the same as the first time. So if you have some file in an S3 bucket, and you want to use ROS3 to read it, you can do that in Python or through a C program, whichever is easier for your use case. And the last thing I'll be covering briefly today is H5 Coro. So, well, you can use ROS3 and you can use HSDS to read things over the cloud. There are a couple ways in which, the default library IO patterns aren't optimized for, cloud data. The primary way in which this is true is caching. If you want to read something from a file system, it's relatively fast, so you don't need to cache a whole lot of data. But if you're going over the network to an S3 bucket, you prefer to read ahead much more to avoid as many small requests as possible. And so by making changes like this, as well as a few other things which are more complicated, the H5 Coro implementation of the library can achieve much faster performance with HDF5 files on the cloud than other methods. Unfortunately, we don't have an example of using H5 Coro set up yet, but it's planned for the near future. And that covers all of the HDF5 tutorials that go over cloud material. I'd be happy to hear any feedback or comments or questions anyone has about this cloud content or about the tutorials themselves.
About others may be thinking, I think one thing about H5 Core to point out is that it is not a complete reader of HDF5 file format. It actually, H5 Core has no dependency on the HDF5 library. It's completely independent. And it only can read certain things like one-dimensional data sets and things like that. It's highly customized to a specific NASA satellite data products from which that H5 Core software was developed for.
Right. It is its own separate, completely separate implementation of a subset of the library for a particular use case. So I think when we implement an example of it, we'll have to explain that so that people understand, what it's for and what it can do. All right. If no one has any more questions or comments, I think we can wrap this up.
Matt, I have one question. This is Robert. Um, if in your if in the HDF5 file that you stashed on S3, there's nothing to prevent that from containing external links that would point back to a file that you're keeping local. Do I have that right? It would be the responsibility of the application program to set the necessary file access property lists, but there's nothing to prevent that. Is that right?
Yes, that's right.
And would the same hold true for if I were going through the RESTful to HSDS?
I believe the RESTful by default, if you create multiple files through it and use external links, it will automatically use the RESTful to access the external files. But in principle, yes, you can have situations where cloud files have external links which were originally created to point to local files. That's something that applications have to be aware of.
Yes, yes. So you would need a provision for the application program that's using the RESTful or S3. You would need a provision to determine where that file might actually reside. If I have this right, maybe it's just something I just wanted to sort of walk through the way an external link might be handled by an application that would be using S3 for like maybe some of the larger stuff, but maybe there's things that it would like to hold back.
Mm.
Okay. All right. Well, I'll explore that a little bit more, but thank you. That was very good.
Thank you. It's a good question. Because I know that HSDS has its own particular implementation of external links, which depends upon the domain structure.
Yes, so it's going to be a little different than an S3 than looking at it if the HDF5 file were on S3 using the read-only S3 VFD. It's going to be a little bit different there, as I understand it from what you said.
Yes, a library cannot handle gracefully what you're requiring. Basically, that this is the one of the places where definitely library would have. I mean, we have to decide is it possible or not possible, and how difficult that would be. But yes, if you have a bunch of files on a file system and you carefully set up external linking between them, and then you just move some of them into S3 or all of them, it's not going to work. The library is right now very sensitive. You basically have to know upfront where the file is to set up everything before opening the file. The library is not capable to look at the file's link, the URL, and to configure itself by just understanding the link itself and what needs to be done. You have to set up all manually.
Okay. All right. Oh, that's interesting. Okay. Thanks, Alexander.
All right. Any more comments or questions?
None from me, Matt. That was very good. I appreciated that.
Yep.
All right. Thanks, everyone. We do want to, reiterate, feel free to jump in the repo for the HDF tutorial. We'll post links in the forum for that, but it's with all the other GitHub repos to make comments or raise issues or make changes. But thank you, Matthew, for stepping in today and presenting that. And next week, we'll have Alexander to present. So we'll see everyone next week. Thank you.